So we're going to talk about data encoding, which is pretty simple stuff, but very important. Encoding is what you have to do. In the simplest case, you have to encode everything because you have to turn it into binary data. So if you have letters, you have to run it through something like ASCII to turn it into series of bits, but there are many other ways to encode data. And so malware often obfuscates data, which is simpler than encryption. It's where you scramble it a little bit so it's a little bit hard to read. It's not really encrypted in the sense that you can't break in without knowledge of a secret key or anything, but it's made to be a little scrambled so it's harder to read. And this is often something you do just to slow down analysis. So if you just run strings on it, you won't see the command and control domain right there in the strings. It'll be scrambled somehow. And this is a way to hide strings and hide suspicious strings so people can't tell what your malware is doing so easily. So this is why I was surprised these old ciphers, which I thought would have no place in the modern world, still matter for malware. And unfortunately, they're used by a lot of other software from people who are just too ignorant to understand that this is not a way to really protect data. So they're simple ciphers. If you want to scramble the strings in your malware so you can't just see it with the strings tool, you could do something stupid like the Caesar cipher, where you move every letter forward a couple letters in the alphabet or something. And that does make it a little harder to read the strings. And you might wonder why they don't do something really strong, like AES encryption. And the problem is that's kind of a big routine. You have to import a library and all that jazz, so it's going to make your malware a lot bigger. It's going to be easy to detect because you're importing a library and so on. So often you don't want to do real encryption, but you want to do obfuscation, a little bit of scrambling. So Caesar ciphers, the simplest one, just move every letter forward a few spaces in the alphabet. So attack at noon turns into this junk. That will stop some attackers. It's a very weak defense, but it does mean that people that don't know anything more than run strings will not see the strings. XOR is a small step up. Simple XOR, you have a 1-byte key, so you just keep encrypting it with the same byte. All you do is, let me line these up correctly. Let's see, there we are. All right, so now that they're lined up correctly, if you don't know XOR, XOR is very simple. Let's see, it's this one? Yeah. All right, the way XOR goes, you have the data and you have keys. The key is a series of bits. So this is 3C in hex. And what XOR says is if you have a 0, you leave it alone. So these two bits stay the same. If you have a 1, you flip the bits. So these 0, 0 turn into 1s. That's all you do. So you flip the bits where there's a 1, leave the others alone. And by flipping some of the bits, it changes into completely different stuff. And you decrypt it with exactly the same process. So it's simple. And there's the example. Attack at noon will turn into this garbage. Bracket, HH, bracket. A lot of characters in ASCII, when submitted to XOR encryption, turn into unprintable things like del and FS, which is a forward space or something. And if you do it a second time, it undoes itself. If you're a mathematics, you can see the truth table up there. 0 XOR 0 is 0. 0 XOR 1, you flip it and turn it into 1. 1 XOR 0 changes, and 1 XOR 0 doesn't change, and 1 XOR 1 does change. So XOR is a common mathematical translation that's used in real encryption, like AES, but by itself, XOR is too weak to be considered encryption. One of the many things wrong with XOR is if you XOR 0, it XORs into the key, because the bits of the key that are 0 don't change, and the bits that are 1 do change, so 0 turns into the key. And many files, like Microsoft Word documents and executables, have large regions of 0. So if you XOR an executable, a GIF here, it's all full of 12s, and the key is 12. So it's blindingly obvious what the key is by just looking at it. So that creates an issue. This is an EXE, by the way, not a GIF. But that's the MZ at the start that turns into HB. So there's an example. If you want to reverse single byte XOR encryption, there are only 256 possible keys, so you can just try them all and then find the one that has the MZ. This is MZ at the start, and that's the one that makes it executable. Right, executables always start with MZ. And so that's what it looks like when you decrypt it. Like I say, since it's full of zeros, those reveal the key. Here's what it turns into, MZP. And then it's going to have this program cannot be run in MS-DOS mode, which is the usual thing. So there's Lenny Zeltzer has written a tool to examine it. It's pretty easy to reverse it yourself in Python and so on. So you can create signatures that just XOR the file and look for common strings and see if there's a key that will make a common string. If you have single byte keys, it's not that hard to make a tool that will automatically reverse things. So one issue here, like I said before, is that the nulls make a problem because they make the key stand out. So what people actually use in malware frequently is null-preserving single byte XOR encoding, which is where you use XOR, but there are 2 bytes you don't change, zeros and the key. So you leave the zeros alone and you leave the bytes that are equal to the key alone, and you XOR all the rest. So that algorithm will make it less blatantly obvious what the key is. The zeros will just remain zeros. So that's one kind you'll commonly see. And there's the example. Here's normal XORing. It's all full of 12s. But if you do null-preserving XOR, the nulls are left alone. And now there is no obvious way to tell what the key is anymore. You're going to have to try all 256 possible keys. Now you could have more than 1 byte in the key, and that would make it harder to break. But people often use just a single byte, and this is like the Caesar cipher. It just scrambles strings so you can't see them easily, but it's not really hiding it from anybody that tries to find it with any knowledge. But that's all any security measure ever does, is raise a little bit of a barrier so a certain number of attackers can't get over the barrier and only the smarter ones get over. And this is a weak barrier. So you can look for this stuff in IDA Pro. If you look at the assembly language, you can just look for XOR commands and then look what's around it and try to figure out what it's doing. If it's very simple, it'll just have the key right there as an obvious literal string, XOR everything with 12. That's the simplest kind of single byte XOR stuff, and you might spot that. All right, so you can XOR a register with itself. Now if you see that, that doesn't matter. That's just the most common way to make a 0. That's the shortest way in assembly language to fill EDX with 0 is XOR it with itself. So that does not indicate XOR encoding. XORing a memory or a register with a constant is single byte encoding with a constant key, and XORing a memory reference with another memory reference might be a more complicated encoding, like a multi-byte key, where it has one index counting through the key and another index counting through the plain text. All right, so here's an example of a single byte XOR loop. So here's, I'm seeing that 12 in there. Where's the XOR? Here, XOR. All right, why am I not seeing it? Where is the XOR?
It's on in the function. XOR function.
Where is it?
Second function to your left.
It's in there? I don't see it.
Yeah, it's the third one down, third instruction down.
Oh, there. Oh, okay, great. So that's filling it with 0. That's the one that doesn't do anything. This is the one that actually does it. Okay. That's because this tab filled me. This is the XOR. EAX, that just puts a 0 in EAX. But this is the one that XORs everything with 12. So it's going to, so what the rest of this junk does is load. Yeah, this takes the data you want and put it in EAX. It puts it only in AL, which is the lower 8 bits. So this takes 8 bits of the data and puts it in here. This XORs it. And this takes the AL and puts it up somewhere. So this ECX is a counter that counts through the data. You load the data, you XOR it, and then you put it back. There's the indirect reference. And ECX, it counts through byte by byte. So that's the looping, byte by byte through it. But that one command that XORs with 12H tells you that the key is 12 and that it's single byte XOR, where the key never changes. All right, so you could just as well use other techniques. You could add or subtract a number of bytes. You could rotate left or rotate right the bits. So you could do the Caesar cipher, which is called ROT. You can have multi-byte keys for XOR, and you can combine these things. And you can have chained encryption, which, by the way, is really hard to decrypt, where you encrypt the first byte, and you use the encrypted byte as the key for the next byte, and you use that for the next byte. That stuff is pretty miserable to decrypt. They had that in the CTF about 6 months ago that was essentially unbreakable. But you can do it. And of course, anything in malware is in principle breakable because you can read the code to figure out what they did. But it might be a hassle. Then there's base 64. Of course, base 64 is really important because it's a way to encode binary data as text that you can handle more easily. All of them use the same 62 characters, uppercase, lowercase, and numbers, and then they use 2 more marks to get up to 64. MIME, for email attachments, uses plus and slash and it puts an equals at the end to indicate padding, which is kind of unnecessary, but it's there because you have 6 bits at a time, so you must have 4 characters of base 64 to encode 3 bytes, because you have 4 6s or 3 8s. And so if you have a 5-byte base 64, that means it, let me just draw it up here. It's easier to draw than to talk about that way. Okay, so I have, say I have 3 bytes here, and each one of them has 8 bits. So the first character of base 64 has got the first 6 here, next one has got the first 2 here and the first 4 there. This one's got 4 there and 2 there, and this one's got the remainder there. So these are 4 bytes of base 64, and this is bytes. So three characters of ASCII will turn into 4 characters of base 64. But suppose you have 5 characters of base 64. That means you have 6 bits here, and those 2 bits are not used. So it doesn't come out even. So the only thing that comes out even is a multiple of 4 characters of base 64. So if you have a thing like this, you would add like 3 equal signs at the end to indicate that it's padded. That's what they're there for. And you don't really need them, because by just counting the bytes and taking the remainder after dividing by 4, you can figure out how much should have been there. But the MIME encoding scheme requires them. And what's irritating is if we go into Python and try to reverse it, it will complain if the encoding isn't right. So you just go back and try adding equal signs until it quits complaining, and you're fine. I don't know why they bothered. But anyway, that's what the equals does. The equals is what you use to indicate that you didn't have an integral multiple of 4, which means the original data didn't have an integral multiple of 3 bytes. You had something like 7 or 8 bytes of data you were encoding. Anyway, it's just a way of grouping the bytes 6 at a time, so one base 64 character has a couple of bits of one ASCII character and a couple of bits of the other ASCII character mixed together. It's very simple to reverse, and therefore it's not encryption, but it certainly makes things unreadable. And looks like that. You've seen it before. So yeah, there's the chart that shows this. So 3 bytes of input are going to, 3 bytes of input AT&T are going to turn into 4 bytes QVRU down here of base 64, 6 bits at a time and 8 bits at a time to express the same 24-bit quantity. You can do it online, you can do it in Python, it's all over the place. It's a very simple transformation. So there's ATT turning into QVRU. And there's the padding. If you had only 2 characters, then it's only got enough to make the first, that's only 16 bits. So you have 6 bits here and 6 bits here and 4 bits here, and that's all there are. So you have an equals to indicate that you had to have another character that had got up to a multiple of 4. All right. That's the game. If you had only 1 character, you get 2 of these to get up to 4 again. That's the joy of padding, for what it's worth. All right, and so here's an example of a URL and a cookie that are both base 64 encoded. Normally you don't see things like this where you're going to get a page like that, because a page is typically like this. Looks like a directory in which there's a page, and that is of course false. Nobody has a directory with a name like that. This is data being snuck out of the company in things that look like get methods. So it's not really fetching a page, it's just making it look like that. And the thing at the other end is not really a web server, it's a server looking for this encoded data and finding it. So in this base 64 encoded string is something you're sneaking out of there, like a password or something. And you can put it anywhere in the GET request as long as your server at the other end knows, but this will look to the intrusion detection system, like web traffic. Somebody's getting something, unless you have a smarter IDS. And I saw about a year ago a product being developed that would check the entropy of these things. We'll talk more about entropy later, but you can tell that this is kind of random. Longer and more random than something a human would use. Real English has low amount of disorder, which is entropy, and random stuff like this has a higher amount. So you can do a mathematical test to detect that this is not really intended to be read by humans. It's things sneaking out. Anyway, that's base 64, and so is the cookie. And that's a way to sneak data out. There's the cookie, and if you reverse the cookie, you get bot 54164, and this is common when you get infected with bot controls, panic control things. They infect your machine, it now assigns you a code number, often calculated like from your version and date of installation or something, and it assigns you a number, and now you have an identifying number at the other end, so you will appear on a command and control console as one of their bots, and they can issue orders, these 1,000 bots go attack that site, and these bots mine bitcoins or something, and you have to have a unique identifier, so it assigns you a unique identifier like that and sends it back into beacons. So if you want to find use of base64 in malware, you can just look for the indexing string. In order to make it, they will typically make a string that has all the characters in order, capital, lowercase, and numbers, and something like plus or minus at the end. That's pretty easy to spot. You'll find that in there because what it's doing is taking the bits, turning it into a number, and then using that as an index in this string to do the encoding. So decoding the URL shows things like this. Here's, for example, some malware uses these base64 encoded strings, but when you decode them, they just turn into random garbage. That's because one option is to make a custom base64 encoding where you take the lowercase a and move it here. Now you use the same code, but it's not going to be standard base64 anymore. The patterns of bits mapping is different, so that's sort of like a Caesar cipher combined with a base64, a way to make base64 a little bit harder to reverse and stop yet another level of defenders from figuring out what's going on. So there's what you get if you use the custom encoding. Now this turns into readable text at the other end as the malware is sending commands and information back to the server. So I got a few iClicker questions about that stuff. Grab one if you need one. Make this thing the right size. Get rid of that. There it is. Yes. The light is on. Ah, good. A sign of life. Okay. So, which coding reverses itself? All right, I'll quit at 30. I think that's all the answers I'm going to get. All right, and the only one on this list that does that is XOR. Caesar does in the one special case of ROT13 for letters, but the rest of them don't reverse themselves. XOR does, however. All right. All right, which one is easily reversed? That would be E. Looks like the answers are in. And that is, of course, it. They're all easy to reverse. That's the thing about obfuscation. Obfuscation is not encryption. It is very easy to reverse any of them. That's why it's surprising people use it at all. But since people have enough trouble reading assembly code anyway, making it a little bit harder is worth the bother for the bad guys. All right, which one uses letters, numbers, plus, and slash? All right, that's base64, of course. That's what it is. That's why you have 26 letters, and another 26 or 52, and 10 takes you to 62, and 2 more takes you to 64. That's how it works. All right, what coding turns 3 bytes into 4 characters? It's sort of harmonious out there. Anyway, that's base64 again, of course. The rest leave the length unchanged. Yeah, I think just these things are loose because I don't think there's anything we can tighten up. I think I've tried before.
Yeah, but it usually doesn't make it even when it's this windy.
Yeah.
It must be a baffle or something left open on the.
Yeah, it's hard to guess. Anyway, which one is it has a special problem with zeros? I've had it in here before. It's a certain condition of wind, like direction and speed or something, that causes this.
It sounds like bees or like slowly letting air out of a balloon.
It does, yeah. Anyway, I'll quit at 45 or 6, whichever comes first. All right, and that's XOR, because if you XOR a null byte, it turns into the key, which creates a problem. So XOR has a special condition where it's probably wise to dodge the null bytes. All right, then there's common cryptographic algorithms. This is strong cryptography that really works, like AES and RSA and such, and SSL uses them. This is real encryption where nobody can get in without the key, as long as the key is long enough. So you can do this. If you have symmetric encryption, though, then you have now a key that you have to hide somewhere. So that's a problem. And of course, your malware has gotten larger and you had to import a library and so on. But if they're going to do this, you'll find strings that tell you it's imported the OpenSSL library, which will make it pretty obvious. I certainly find this with Android apps. I can just, once I see something like an encrypted password stored on the phone, I can just search for common algorithms and I'll just find strings telling me which algorithm they're using. And I must say, malware and Android apps have a very similar problem. There's a right way to do encryption on a phone. You use the key store that Google wrote, but they don't use it. Only one app in 100 does that. All the rest use symmetric encryption, and then they try to hide the key on the phone where you won't find it, which is pathetic. You have this secret key, and where are you going to put it? And if you're malware or an app, there is no good place to put it, and you should never use symmetric encryption in the first place. However, malware authors, it makes more sense, because even if they just put the key hard-coded into malware somewhere, that's again going to confuse some researchers. So Microsoft crypto functions, we'll start with crypt or CP or cert, so you'll see them here. Here's crypt, acquire, context, encrypt, decrypt, encrypt, encrypt. So you'll see if they're using Microsoft libraries, you can spot them that way. You can also search for common cryptographic constants. A lot of cryptographic procedures require certain numbers. And there are magic constants, binary signatures, that work pretty well. The only problem is RC4 and IDEA do not use a magic constant. So there is nothing to search for that will always find it. RC4 is commonly used, the stream cipher. Same thing is used by WEP. It has some security problems that are causing people to move away from it for things like HTTPS, but certainly for malware it's good enough. So here's find crypt looking in there, and it's finding constants used in DES. So this malware is apparently using DES. And by the way, remember, DES is not safe with the old 56-bit key, but again, we don't care. It's malware. It's just trying to scramble things. It might use an old weak algorithm because it's not really hiding secrets in the customary way. It's just trying to make it harder to analyze the malware. There's a PEID plugin that will try again looking for base 64 tables and other crypto functions, another tool, canal you can use. And then there's Entropy. Entropy is a measure of the amount of disorder in something. It applies to the universe, it applies to information in general, applies to everything. The point is, if you have something like a glass of water, it's in a nice ordered state, but when you spill it all over, you can't put it back in the glass easily. Everything moves from a state of low entropy to high entropy, and that's what makes time. But as far as we're concerned, we're only concerned with information theory entropy. And the point is, you might have 100 bytes. But the question is, how much information is there in 100 bytes? If the 100 bytes are all 0, there's actually no information in there at all. If the 100 bytes are all ASCII text, there's some information in them. But if the 100 bytes are all random, there's the maximum amount of information. So when you compress something, you randomize the bytes. And you have a higher degree of information in there, and that's the point. You shrink something down as far as you can shrink it. It can't shrink anymore with things like zip. That is increasing the amount of information stored in the bytes. And that's the game here. So if you have completely random bytes, the entropy is 8. That's the number of, that's what you call it. There's 8 bits of data stored in every byte. No bits are wasted. If you have, the bytes are all the same, the entropy is 0, because there's actually no information in there. The thing could be shrunk down to size 0. And that's the game. So you can do it in binwalk in Kali. I don't think I'll do it. I'll just show it to you. Here's a simple Python code that does this. Makes 10,000 random characters. Then it puts the base 64 encoding, the base 32 encoding, and the base 16 encoding of that, and then 10,000 characters that are all the same. So the random characters have entropy of 1 on this scale because it's 1 bit per bit. It would be 8 if you're using the same measure. So the maximum entropy is random stuff. Base 64 has an entropy of 6 because you're only using 6 bits. Remember, there's only 64 possibilities for each byte. You're only using 6 of the bits out of each byte in base 64. Base 32 only uses 5 bits. Base 32 is a real thing, by the way. You don't hear of it much, but it's important in DNSSEC. They use a lot of base 32 encoded stuff. And base 16 encoded stuff is just hexadecimal. There's only 16 possible values for each byte, so you'll only have an entropy of 4. And here's everything is just A's, the entropy is 0. That's what entropy means. So if things are encrypted or compressed, the entropy will be very high. And if they're wasting space, then the entropy will be lower. So you can concatenate some images. A bitmap is here with low entropy because remember, bitmaps are very big. I can have a whole square of white and it will just have white, 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 many bytes all the same, so that's low entropy. But a GIF is a compressed format, so it's got high entropy and so does a JPEG. Those are compressed so they don't waste any space. They've started with this and squeezed out all the wasted bits, so the remaining bits are used completely. It carries as much information as it possibly can carry in that number of bits. So IDAPRO has an entropy plugin that will show you the regions of high entropy. So here you see the entropy. This reads the text is entropy 6, like base 64. The data is entropy near 0. This is 1.5 or 1.3, and here's more details of areas near 6. This is one way to get some very general clue of what's stored in there. So here's some common parameters. If you look for 5.95, you found base 64 encoded stuff. It's got 6 bits of data in every byte. If you find entropies like 7.9, you've got random stuff. This is stuff that's compressed or encrypted typically. And you can make a graph of it and hover over the graph. So I hovered over a point here at 6.9. The brightness tells you how disordered it is. So the dark areas are areas that have very little information, just like a bunch of zeros, and the bright white areas are areas that are compressed or encrypted. So it's one way that you could take data and try to find what part of it is interesting. All right, and here's an example of an entropy graph for malicious executable. So it's going from 4.8 to 6 here, and you see the areas of high entropy indicate something interesting. This is something encrypted, that's why the entropy is high. That's the DES constants up there, so it's got some numbers that appear to be random. And this they call the coda, I'm not sure what that is. But anyway, it is, as you can see, if you have just a block of malware and you don't know what area to look at, this is just another way to find some spot that is different than what's around it and therefore worth a look. It's very crude, it's just one number. You know, it's not telling you too much, but it might help you find an interesting area in malware. And then there's custom encoding. You can make your own homegrown encoding scheme. In general, it is a terrible idea to make up your own cryptography. You should never do it if you're actually trying to protect data, because everything you can just dream up in the shower turns out to be something someone else invented 200 years ago and broke. But if you're a malware author, it's perfectly fine if it's not really cryptographically secure. It just has to be a little bit confusing to confuse the good guy. So have a round of XOR and then a base 64 or something like that. So here's one. This malware is going to use, you read the code to figure out what it's done. Here's these bytes of encrypted file, and there's nothing there to give you much of a clue. So if you look at the, let me get this thing out of the way. Won't move as usual. All right. So if you look here, it calls create file, and then write file. And here it uses XOR with a pseudo-random stream. So here I'm seeing the XOR, EBX to EAX. And here's going to be, one of these is going to be counting through the buffer. This is going to end, this looks like the pseudo-random creator. Yeah, so here's the thing. It's going to this is going to be the pseudo-random function that scrambles the bits to create something somewhat random. Then it's going to take only the lower 8 bits of it by ANDing it with FF. So then it's going to put that, and then it's going to XOR it with EBX and move it back up here. So I'm not going to get too much into the details, but the point is you have a pseudo-random stream of bytes, which is then used to XOR. Each byte is different. This is how WEP works. WEP has a pseudo-random series of bits, and it XORs the bits with the data on the way out. And if the pseudo-random stream is random enough, it's a strong form of encryption. Here it just depends on what you use for random number generator. And there are plenty of random number generators that are very simple and start from a seed. And if you just remember the seed, you can create the exact same pattern of random numbers again. So it's a way to use something that's going to be a little more complicated than single byte XOR encryption. You really will have to read the code to figure out how to reverse it. And that's the game. Custom encoding can be small and non-obvious and much harder to reverse engineer. You can't use a simple tool like the one we talked about before that would try to use single byte XOR encoding and find common strings. It won't do you any good here. The only way to do it is going to really be to read the code and figure out what it does. And that'll again stop the people that aren't trying pretty hard. So to decode this stuff, there are two general ways to do it. I've been doing this for Android apps for a couple of years now. The simplest, there are two techniques, and they're both useful. If you can understand what it's doing, like you find it using a standard library like AES or something, then you just rewrite it in another language you like Python. Write the code that reverses it or does the encryption to prove that you've got it. The other thing is you can just use the malware itself. Find the function that does encryption and jump to that function. Use it. You don't even need to understand it. I do that quite frequently when dealing with obfuscated PHP. You get these long, irritating functions that are hard to figure out, but I don't really need to figure them out. I can just use them as they are. The only problem is, in both the case of PHP malware and binary malware that we're talking about here, if you use functions from the malware and you make a mistake, it might do something malicious. So, of course, be aware of that. When you're going to use pieces of malware, you ought to be doing that in a disposable virtual machine. You can stop the malware in a debugger at the point where it has decoded the data and find it there. Then you can find the decryption function. This is sometimes possible. Sometimes it's too hard to find a good spot to stop it. I know I've been trying all these techniques. I'll look at the encoded data and just try a few transformations to see if it's something simple. Then if that doesn't work, I'll try to find the routine that wrote the encoded data on the phone. So I find the name of the variable that it stores on the phone and look for that name as a string until I find the code that wrote that and see if I can figure out what it was writing and follow it. And then if everything still doesn't work, I just try to find known encryption routines by looking for the strings involved in them to see if I can get them. And you just keep hunting with every technique that comes to mind until you find the code that does it and you find out what's going on.
Can you find the key?
Often I can. In quite a few phones, the key is just written in plain text, or there's just a plain text password that's hard-coded, which is then run through something like PBK DF2, which is just a bunch of hashing routines, like 5,000 rounds of SHA-512, followed by taking the first 128 bits, and that's the key. Other times, the key is actually stored in the file, too. One of the base 64 strings is the key. One of the base 64 strings is the encoded password.
I mean, with a malware, you have the piece of software. How can you hide the key inside the piece?
Well, see, you could...
Lock the key, right?
Well, you could just have the key as a fixed constant in the data section, just sitting right there. That would be the simplest way. You could have some kind of code word which is used to construct the key, like that XOR stream we had. You'd have some kind of seed, which is then run through a pseudo-random number generator, so that would just be hard-coded. The other thing you can do is you can construct the key from things you can find. I know that's what I find on phones. A lot of people use the phone's serial number and model number and something and combine that, hash that, and they call that the key. It just has to be something that you can reproduce later. And you can't really ultimately hide something in the malware that can't be found, but you can make it more and more irritating and tedious to find. That's all you can do. So it's just sort of like a little brain twist teaser. That's why I do it. It's better than crossword puzzles to figure out how Android apps work, by digging through them until I find out what stupid technique did they use to hide the key this time. And I've seen 3 or 4 stupid techniques used. It's ultimately stupid, though. But in malware, it's not that stupid because you know that it can be reversed. You're just trying to make them work. It's sort of like a defense attorney. You know your client is guilty, but you want to make sure they work. And that does mean it'll take them longer to figure out your malware. So that's the game. You can also manually deprogram it. There are a lot of constant functions. If you There's a string function, base64 in Python, so you can totally decode things in Python. By the way, this is a really hard way to do it in Python. I'll talk about this. This is something I didn't learn in any textbook. I just learned it from Stack Exchange. I was reading Stack Exchange, how to convert things into base64 and hex and back, and I found out that the normal way people tell you to do it is just really, really painful. And you don't need to do it at all. So let me just point this out. Python. Okay, here's Python. In Python, you don't even need to write code. If I write 2 plus 2, it prints 4. This is great. You don't even need to say print. This is why Python is your best friend. So now if I want to base64 encode something, base64 and hex are already natively in language. You don't need to import anything. So if I make a string that is hello, and I want that in base64, I just do a.encode base64. That's all you have to do. Encode and decode on every string. There's the encode. If I want to decode it, I can take that string and decode base 64. And it goes back. That's all you have to do. It is pathetically easy. The same thing works for hex. And I was just doing a phone app yesterday where the password was hidden this way. If my password is secret Fred, they took p.encode base 64. Now that would be too easy, so they then encoded it as hex. And that's what they store on the phone.
That's a big whoop.
So it's not blindingly obvious that that's your password, but it's really this simple to get back to your password. And I just thought I'd mention it. Python has, if you read how to decode, put things in hex and ASCII and base64, it looks hard in Python, but that's all it is. Encode and decode functions just right like that. It rocks. And we'll be doing a lot of that next semester in the cryptography class. Anyway, so here's some example. Here's Python base64. Here's Python's null-preserving XOR. So you're going through the characters, and if it's equal to the key or 0, leave it alone. Otherwise, return this XOR key, and the caret is the XOR command. So it's very easy to do this stuff in Python, and that's how I always do it. Rewrite in Python. It only takes about 4 lines of Python to do any kind of cryptography you want. So here's a custom base64 script. The real base64 is down here, so the custom one starts with 9 and Z and leaves all the rest alone, but that's enough to make it totally different. So here's what I was mentioning before. You go through your ciphertext, you just find the location of the character and find it in the base64 string, and that's what you put out. So it's a couple of strings, you hunt through that character to find where it is, and that's what you put out. You take the bits. All right, there's PyCrypto is a library for this stuff. This is what I've been using a lot, Crypto Cipher. You can import DES, AES, RSA, and all the good things, and just run them, and it's very, very easy. It's only a couple lines of Python to encrypt and decrypt anything you want. If you haven't taken the CISSP class, this stuff may be unfamiliar. There are different modes of cryptography. ECB is the simplest one, electronic codebook, where every block of input is separately encoded to a block of output. So if 2 blocks of input are identical, they have identical blocks of output, which means some patterns in the input are preserved, and this is considered a very insecure way to encrypt things, but it does scramble things. It's cipher block chaining is the recommended technique most people use, where each block is used to construct a nonce that's added to the next block, so it's different. So if you have identical blocks of input, they will not produce identical blocks of output. But ECB is the simplest technique, so-called textbook encryption. All right, so here's how you do it in malware. You set up your malware debugger. You get your encrypted file that you're trying to read, and then you allocate memory so the malware can reference it, put the encrypted file in the memory, and now you set up the malware, the variables and arguments to run that part of malware that goes through a file, point it to your file, and use the existing malware functions to decrypt your file. This will be possible once you have isolated what the functions do. And as I mentioned, if you make a mistake, you will end up running the real malware and doing something malicious. So always do this stuff in a disposable virtual machine. That has happened to me with PHP malware, where I deobfuscated it and found a part, and then I thought this part was safe to run, and I didn't notice that one of the malicious functions was still in the part I thought was safe. So it's easy to make that mistake. Be aware. So here's a decryption script for immunity debug. They've actually written a script in immunity debug. Remember, you can do this. You can write Python scripts and add them to immunity debugging. So we haven't talked about, you haven't done it in your projects here, but you can customize immunity by adding Python to use immunity. And here's an example of how to do it. I don't plan to go through it in any detail, but it is a thing to know that immunity is extensible. By the way, Wireshark is also infinitely extensible, but you have to write Lua, whatever the heck that is the language they like. Immunity uses Python, which I'd much rather do, but in both cases, if there's anything you want them to do, you can totally write your own script and add it in. That's what Mona is. Anyway, all right. So I got some more eye clickers, and I think that's it. I said not that much in this chapter. So, which technique is so weak it's not even considered encryption at all? The technical term for this stuff is obfuscation, where you make it a little hard to read, but you haven't really hidden it from anybody that knows how to do this stuff. And that's, of course, base 64. Base 64 doesn't have a key. It's not encryption. It's just grouping the bits 6 at a time instead of 8, so it's trivial to reverse. This, by the way, is true of Cisco encrypted passwords. In our earlier configuration files, this is how I found the password for Kaiser Permanente Hospital, VPN. I taught my advanced hacking class for the first time, and they said, if you just go in Google and search for file type PCF, you'll find Cisco configuration files. And they contain something called encrypted password that's like 50 characters long of garbage, but it isn't really encrypted. It's just obfuscated. You can totally reverse it in Kane, and I did. And I found the Kaiser Permanente configuration file up there with what was obviously a secure password, and I found a way to quietly inform a friend of a friend that somebody should know up there. And that was when I told a journalist about it, he said, I asked my friend, and he said, it doesn't matter because that password is not a security boundary. And I'm like, the password is not a security boundary. You know, that's what they always say. Like, if you look at the ads for Cisco, Cisco first invented VLANs. And they totally said, VLANs will segment your network and make it more secure. Buy them to improve your security. And then people figured out how to hop VLANs. They said, they were never supposed to be a security boundary. This is how everything always goes. They advertise it and sell it to you, and then when it's broken, they say, oh, no, we never intended for it to make secure.
Temporarily, it's supposed to keep you secure until someone finds a way around it. Isn't that the...
That's really all any security is. No security is perfect. It's just a fence that stops some attackers. That's right. And after...
Companies the size of Cisco, too, have, like, once you talk to the engineer, they're like, oh, yeah, of course we never designed it that way. The marketing team was the one that was like, oh, yeah,
Well,
this is so secure.
Well, you know, what happens almost invariably is people bring out security things, and then they get hacked, and then they find that they're less secure than they were supposed to be. But anyway,
It's like better than nothing, right?
sometimes and sometimes not. Sometimes you're just totally get ripped off. Like the first generation of encrypted USB sticks, almost none of them are encrypted. All they did was put a little code on it, so when you plugged it into a Windows machine, it would pop up a box and ask you for a password. But if you just use DD in Linux to take off the data, it's just right there. So they made it look encrypted, and they made it so if you just plug it into a Windows machine, you can't just immediately open the file and see the data, but they didn't actually encrypt the data until the next generation came out, except for the high-priced ones like IronKey. IronKey was really encrypted, but the rest were just fake. And that's true of almost every security device.
Did they sell them as encrypted or as password protected?
Well, that's a good question. I know, that's a good, if they may not be prosecuted by the FTC, but it certainly is true that the customer was not really getting what they had reason to expect they were getting. And that's usually the case. That's why they want me to do a webinar tomorrow on DDoS, and I was talking about that. People said, what can a home user do? Now they're going to have smart light bulbs and smart thermostats and all this jazz that they don't understand. That's all vulnerable. And yeah, it's a webinar in Britain, but I'll be doing it tomorrow morning. It's some reasonable time in Britain. And I said, what can an end user do? And I said, the main thing, as far as I know, the main thing an end user can do is understand that they are beta testers. This is the first generation of this stuff. It is all full of flaws. You can expect it to have problems. You can expect to have updates, product recalls, replacements. Be aware of the fact that if you don't want all your stuff getting hacked, you probably shouldn't buy the first generation of smart light bulb. Wait a couple of years and let some other poor slobs get hacked.
You say the same thing about Microsoft.
That's right. That's right. The first version of it is going to be all full of bugs, and right now they don't even know about security. By the way, the one thing I found, I've often recommended this. that we should have cyber UL listing, and I just discovered this has actually been around for almost 6 months. UL, the same people that rate your products for electrical safety. The original purpose of UL was to tell you if your toaster and vacuum cleaner and everything was going to shock you. Underwriters Lab, they have a cybersecurity standards now for network connected products. This has been out for like 6 months, so you can actually have a UL label on your product saying it has been certified cyber secure by Underwriters Labs. And if I don't think you can buy real products with this on the app, but this is a really good step forward. You should be able to see some kind of label on the box that gives your end user some clue whether this thing is absurdly insecure or not. And it looks pretty good. So I don't think anybody's doing it yet, but here's what they say. You should have fuzz testing. You should make sure it doesn't have known vulnerabilities or malware on it. Do binary and static analysis. Have access controls. This is basically the OAuth top 10. They say you should do all that to get the rating. That sounds pretty good. I don't know how it's going to work out in practice, but this is the real step forward. There should be something on the label that we can tell that gives the end user a clue whether they're buying junk or not. Anyway. Yeah. Yeah, I don't know if they have an icon. Let's see. I think it's just this thing, right? UL? That's what it is. But here they have series of standards and everything, and supposedly all this good stuff, smart cars, medical systems, fire alarms. That would be awesome if you could buy the UL rated version of all these things for a little more money and then feel safer. We'll see if that actually happens. Anyway, got a few more of these. Which one uses names starting with CP? All right, I see the 6 are in. That's the Microsoft crypto functions. All right. And I said, and there we go. All right, which one is particularly difficult to detect? I'll quit at 30. All right, and that's RC4 because it doesn't use any specific constants or instructions or anything. The XOR, you can look for the XOR instruction. These guys have magic constants you can look for. This thing has that characteristic string, A, B, C, D, E. This doesn't really have any particular signature you can count on finding. All right.
Should have known that because I don't really know RC4.
Yeah, you don't know because it's not that simple. Yeah. All right, so if a file contains random bytes, what's its entropy? I'll quit at 30. All right, there. The entropy is 8, which means every byte contains 8 bits of information. It is packed as full of information as it can get. There is no way to compress it and make it smaller. There's no patterns to exploit. That is highest entropy, the most information stored, which is 8 bits of information in every byte. All right. If you have base 64, what's the entropy? All right. And that's 6. There are 6 bits of data in every byte. That's the point of base 64. It's only encoding 6 bits at a time. 2 bits are wasted, and that's why it has an entropy of 6. All right, so that's it. I'll stop the recording and see who got the most right. Here, this is 126, chapter 13.